Now that we've done our initial simulation setup, let's add some collisions from the building and from the monster. So if we dive inside the DOPNet, we can add another volume source for those collisions. I'll start by just adding one for the building. And in the initialize parameter, we're going to select collisions from the dropdown. Now this is going to set up a source volume and target field called collision, and you'll notice that the scale is set to -1 because typically we're passing in an SDF volume for these collisions, and the data formatting for an SDF is the inverse of what you would see with a normal fog volume, which is why this is set to a scale of -1. And this operation is set to maximum, so that when we merge in multiple collision volumes, it just takes the maximum value of those overlapping collision areas, so that the collision areas will all merge together nicely into one collision mass. And for the velocities, you'll see that it's looking for a volume called V from SOPs, and that's adding it to the collision vel field in DOPS here. This name is very important because our pyro solver knows to operate on this field called collision vel in order to apply the velocity influence from those collisions, so this has to match exactly. You can call your field in SOPs whatever you want, as long as your name in SOPs matches the name specified in the source volume here. And the same thing is true for our collision field and the DOPNet. The target field has to be called this name precisely, but in SOPs you can call the field whatever you want as long as that matches the source volume name here. So I'm going to rename this to volume source building and attach that to the merge. And we always want to make sure that the camera is the last volume source in the merge order. It doesn't matter too much if the camera comes before or after your collision fields because they're writing to different target fields in the DOPNet. It's just important that the volume source comes after any other density fields that you might have volume sources for. And it's just safer and easier to remember if you always make this volume source for the camera last as a rule. Now for our building collider, we don't have any source volumes to point this to yet. So let's jump out of our DOPNet and create those collision fields. And we can start by merging in our RBD sim from week 5 post sim tweaks and out final fracture. And we don't need to collide with all of the little pieces in the RBD sim, so we can use our measure fracture HDA to remove those. So we can drop that in, connect it to our RBD sim geometry, and we don't need to recalculate the bounding box size because that attribute already exists on our incoming geometry. So you can uncheck that and turn on the bounding box size filter. And then we can give this a low size threshold like 0.003 to only remove those small pieces. Now let's add a null. I'll call this collide pieces and connect that to the second output of the measure fracture HDA. And I don't really trust calculating this velocity or those angular velocities because as I've experimented with it, I've noticed some weirdness in the way that the angular velocities are calculated by the trail SOP. If we take a look at this example where I've created a packed box and just used a transform SOP to spin that around on that Z axis, it looks like it is creating some angular velocity for us, but it doesn't look quite right. If we take a look at this in the middle of its spin, we should be seeing those angular velocities in the direction of that spin, but it looks like they're actually off axis and spinning in a different direction as well. And if we change our temp normal direction to point on the x-axis instead of the y, it will still give us some angular velocity, but it will be a bit different and still incorrect. Whereas if we do a regular velocity trail on this unpacked spinning geometry, you can see this is what those velocities should actually look like. So it looks like this trick where we add that temp normal and trail the angular doesn't work very accurately. And for our volume colliders and the dust sim, I want to make sure that our velocity influence is pretty accurate. And because I don't really trust that angular velocity calculation, it would be a good idea to change this in our density source as well. So instead of calculating the angular velocity on our transformed pieces, we can pull out that trail SOP and turn off the angular velocity, and then just use this to calculate the linear velocity on our simulation points. So if you display that, you can see the velocities are being added to all of our sim points here. And we won't need this temp normal anymore since we're not calculating that angular velocity. And then on our transform pieces, we can set the point velocities to instantaneous point velocities and check our unpacked geometry to see what those velocities look like. And zooming in on some of these moving pieces, it looks like these velocities are still pretty accurate, even if it's not taking the rotation of the pieces into account, and this should be good enough to fill in those gaps in between the frames so that we can avoid that stamped density effect that I described in our density source video. Now getting back to our collision volumes, we can unpack this geometry and then trail it to make sure that we have super accurate velocities on all of these pieces. This has to be a bit more accurate than our density source did, because the density source really just needs to make sure that it fills in the gaps in between the frames, whereas the velocities in our collision volume are going to really influence the motion of the sim. So when we have big spinning RBD pieces, we want those spinning velocities to be accurately reflected in their influence on our dust sim. Now after unpacking the building geometry, let's convert that to raw polygons, and then we'll use a trail SOP to compute the velocity on this. Now we're also going to want to collide with the windows, and those aren't currently included in this RBD geometry here, so let's object merge those in. We can pull those in from week 7 shattered windows, and then the intact windows null. And we probably don't need to collide with all of the windows that are outside of our main destruction area, so we can add a blast SOP and type in at active frame is greater than 1150, and then flip the group type to points, and that will get rid of all the windows and the static portion of the building. So we just have the windows that we actually need to collide with. Now colliding with very skinny objects like this, sometimes it's not very accurate, and the VDB from Polygon SOP can sometimes have a hard time representing these very skinny surfaces. So let's unpack our windows, and we'll add a peak SOP to those to thicken them up a bit. And it looks like a peak distance of 0.1 should be a pretty good starting point for thickening up those windows for collisions. And now that we've improved the collision shapes for those window panes, we can merge that with our building geometry. And it's okay that the building geometry has this trailed velocity data, but the window panes don't, because these windows aren't moving at all, and when we merge that with the building, the windows will just pick up a default velocity of 0. And now that we have our building and windows merged together, we can use a VDB from Polygon SOP to create our collision volume. And I'm going to make that VDB a little bit higher res than the default. I'll change this voxel size from 0.1 to 0.07. And instead of using this default name of surface, we'll call this collision, because that's what our volume source and the DOP.NET is expecting. And we can turn on these surface attributes as well to copy over our velocity data. So in the attribute dropdown, you can select this point.v attribute, and the vector type will be displacement / velocity / acceleration. And we should also turn on this fill interior option as well. Now, even though we haven't specified a VDB name for this extra point velocity attribute, this is automatically using that V attribute name as the name of that volume, and our volume source in the DOPNet is already looking for a velocity volume called v, so this is fine as it is, and this will match up with how we've defined it in our dust sim. If you want to hide this velocity volume in the viewport so that you can only see the collision SDF, you can use a visibility SOP and connect that to our VDB from polygons. And then in the group here, you can just set @name equals v. And then if you display that, you'll see that it's hiding that velocity volume and just showing us the collision SDF. Now let's create a file cache for this collision volume and cache this out for the entire frame range from 985 to 1150. And after that cache, we can add a null to reference this into our DOPNet. And I'm going to call this null source collide building. Now it may take a while for this collision volume to cache out to disk. In my case, it took almost an hour. It was about 50 minutes for this whole sequence to cache out. But once that's finished, you can see this loads up very, very fast, and this is going to save us a lot of time over trying to calculate all of this collision volume calculation on the fly. And now that this is cached out, let's go into our DOPNet and that volume source for the building. I'm going to add collide into that volume source name to make this nice and clear. And we can point this SOP path to ... /source collide building. Now I will rewind the sim here, and after that refreshes our simulation, we can visualize the collision data that's been added to the sim. At this point, when viewing the output of our sim, we don't see anything in our volume grid yet. So if you click on the smoke object, we can turn on visualization for the collision. Underneath the guides and this visualization tab, you can turn on collision here. And then if you step through the sim, this will show you the collision data added by that volume source. Now you'll notice that this doesn't perfectly match the volume source that we created in SOPs because our sim is limited to the resolution specified in our smoke object here. So if we turn down that division size to make this a bit more high res, then we should see a better representation of that collision source. And viewing this collision data can be helpful when debugging your simulation, but when I'm not debugging this and just working on the sim in general, I typically leave that visualization turned off. And one more note about the collision settings on this building collision source. I found that in this sim, a scale of 1.5 on those building velocities was a bit too much, so I turned it down to 1, although this is one of those parameters that you'll find yourself spending a lot of time tweaking to get your simulation just right. The amount of velocity contribution that you should use can vary a lot between different shots and simulations.